So in the previous presentation, I talked about some of the basics, and we talked around the subject of how to create signals based on PDWs using our UXG, and analysis using a UXA. Now, what I'm going to talk to you now about is the idea of injecting some kind of target or simulating a target in our system for test purposes. Now, this isn't an EW system. This is us taking data from a device and providing it with a target so that we can test it in a lab environment. So this is what we talk about is a radar target simulator. And in this particular instance, I'm going to talk about using COTS equipment. That's commercial off-the-shelf equipment. So I'm going to talk about some of the trends and why we need to do this, and I think that's kind of self-evident from the previous presentation, in fact. I'm going to talk about requirements for radar target simulation, and I'll give you some examples of how that will fit in. And I'm going to present you a solution that we have in Keysight today that's available today using the tools that are available today in terms of, and Phil already mentioned our capabilities with the Pathwave FPGA environment, and I'm going to talk around that and some of the hardware that we have to use with Pathwave FPGA before we come to the conclusions. So as I mentioned previously, the origins of radar systems and EW, jamming, countermeasures, that process has continued since the 1930s, 1940s. But there are still market forces in play here as well. So it's important that we understand the requirements are not just based on the technological requirements and the technological capabilities of our allies and adversaries. We're also driven by market forces. So part of that market force is the requirement of governments to have dominance of their airspace and for the dominance of the electromagnetic spectrum. To do that, we need to invest, and it's clear that in the kingdom you have this Vision 2030, and that is driving a lot of investment within your country. That investment is driven to increase our technological capabilities and our abilities to defend ourselves. That investment drives development of new technologies and new techniques. And it's very important that those techniques are covered both, not only the radar systems themselves, but also the countermeasures against other systems. Testing such technological capabilities means that from a test company point of view, we need to be offering state-of-the-art technologies for testing. Although there may be huge amounts of investment, we still need to be cost effective. EW, electromagnetic spectrum, dominance is only part of the equation. We need to make sure that the return on investment on development of EW is equivalent or better than some alternative technology that will allow us to say that we need to invest in this technology. So there is a cost constraint, but also a time constraint, because we need to be competitive with the adversaries as well, the adversary systems. So we need to be fast, we need to be flexible, but we also need to make sure that costs are maintained. And part of that cost from a test point of view, as I say, is designing for test at the early stages of design. So considering what our requirements are through the whole product life cycle. All of this drives us towards new testing techniques. From a test and measurement supplier, such as Keysight, we're always looking to adjust our methods to make sure that we provide you with the most amount of data that allows you to characterize and make sure your operational systems are up and available for the maximum amount of time. That means from our side of the fence, we need to make sure that we provide the flexibility and the technical capabilities that allow you to test flexible, high technology devices, including EW. So what is radar target simulation? As I said in the introduction, we talked previously about signal sources. This is something that we can provide based on PDWs. We can provide a radar-like signal to a system under test. That is perfect for looking and getting a data point on the functionality and the reaction to that system to multiple signals. But an EW system is an active system, and so it needs to react to complex scenarios. And we can build scenarios for a signal source and build up complex waveforms and pulse parameters and build into that system, build into that signal a lot of the detail that we can have in an environment. But an EW system is complex, and we need to be able to react and see how it reacts to other countermeasures. So for a given system, we may want to provide some complexity to it during the test. And that's where radar target simulator comes in. And this is basically, as the title suggests, simulating the return signal of a radar system. Now, if it was just a simple CW RF pulse, a radar target simulator would just be a feedback loop. Okay, this would just be, this would just take in the CW pulse and send it back out. That's 1940s technology, and radar systems have got much more complex. There are a number of challenges today. So we need to deal with the notion of radar cross-section, RCS, also jet engine modulation, jet engine modeling, and other models. So we actually, complex modeling of return signals based on what the RF energy that is coming out of our EW or radar system. Into that environment, we may want to add rain, noise, clutter. We may need to look at adding reflections off of terrain, providing multipath return signals, adding Doppler into that. And within all of this, we need to adjust the delay of our signal, so latency. Latency is actually, with radar systems, we often talk about the latency of the return, and that's primarily for embedded EW systems. It's very important. If you think that all of this RF energy is traveling at the speed of light, 1 nanosecond is 30 centimeters. Okay? So 10 nanoseconds is 3 meters, which means if we're looking to change something about an aircraft that may be 10, 20 meters long, we have a question of maybe tens of nanoseconds to react to the radar pulse that's received. With testing systems, that latency is seen as, in fact, how close we can simulate a target. So I'll show you some of the latency we have in our systems today, but basically when we talk about latency with the test system, we're talking about the distance that we can simulate a target. And the lower the latency, the closer we can get a target to our radar system, or simulate a radar target close to the radar system. As I mentioned, the radar systems today are looking to gather more and more data, and we do that through bandwidth and also from the resolution of our devices. So if we have very wide bandwidth, we can get more data from different frequencies. We can get more data points for Doppler and velocity. With more dynamic range, we can detect finer detail and return signals from larger distances. And this is basically what we're looking at. What we have here is a radar target simulator. And this is capturing some RF energy with an ADC. It's doing some processing on that data and then sending out a signal via a DAC. Now, there are various different ways to achieve or build a radar target simulator. The first and probably the most, it's complex, but it's most realistic, is using deployed components. So you can actually build basically a radar system and put that in your lab, right? You can, it might be hard and expensive, but it will have very high performance and equivalent performance to what you would see in the field. However, it's not available to all of us, and it's difficult to calibrate. And if you're looking to simulate other targets, you need to build a new system, so it's expensive. Okay. You can also purchase custom solutions. These are similar to the deployable components in that you would specify the parameters and have build a system based on the requirements. But these can be very expensive and not very flexible. Again, much like the deployable components, you would specify the requirements. And if we're looking at flexible platforms, it's difficult to get that flexibility into a custom solution. It's also, but it's easier to get access to this technology rather than the deployable components. You can actually build using essentially custom, consumer, commercial off-the-shelf components integrated into a system that's much more complex. You can also use our sources and receivers. We're happy to sell you these, but they're not really reactive for use in target simulation. This is primarily, although we can control very accurately the phase and timing within our source, the fact is that with a radar target simulator, you actually need some sort of loop that comes in from what's acquired to what's being generated. And it's much more difficult to actually control phase and timing between different instruments that are connected over a cable. So unless those instruments are integrated together into a hardwired solution, it's difficult to actually get that, maintain that phase characteristics and maintain phase between the systems to really provide the realism that's required for target simulation. So now I'm going to talk about some of our solutions based on some of our modular applications. Now Phil mentioned our wideband solution, wideband signal platform. I'm going to talk about a small system that we have that's currently available today, although the wideband signal platform will be available in a few weeks. So we have solutions for this, but there are a couple of parameters I wanted to cover, a couple of examples, and show you afterwards how we can solve that with our platform. So if we were to test the radar system in a missile, there's a number of ways we could do this. We could launch one of these missiles and see how it reacts to targets. That's going to cost you a few $100,000 per launch. And it's kind of expensive, and it's difficult if you have problems to determine if that's from the radar system or from the missile itself. If we're doing this in a lab environment, we actually want to simulate and use a radar target simulator. So basically what we would do is we would sample the radar signal coming from the radar system on the missile itself. We would down convert that and capture that with an ADC. We would provide FPGA processing, convert that into a signal that we would, within the FPGA processing, we would add some environment, we would add some targets, we could add some Doppler and maybe even some jamming, and then send that signal, upconvert it, and capture and see the output of the systems within the missile radar system. Because we're talking about a high velocity missile here, the importance here is on the latency. Again, we think that the radar, the RF pulses are coming out at the speed of light. What we need to do is make sure that we can simulate a target as close as possible to that system. I mentioned in the previous talk monopulse radars. Again, it's a combination of multiple beams into a single RF pulse. If we were going to test one of these, we would capture all of that, maybe separate that into various different components, but we would down-convert that, convert that to ADC, and maybe send out 4 individual channels of elevation and azimuth out through our AWG. So the solution, one of the solutions we have got today, and this is more for use in educational programs, so to get concepts of EW. So we have a system based around PXI. I don't know if you know of the PXI platform, but it's an industrialized PCI interface. So a very high speed bus throughput and basically a desktop device that we can put in a lab quite simply, and we can put multiple units together into a system, into a chassis. So one of our products here, and so this is the core of this solution, is the M3302A. It's a AWG, digitizer, and FPGA all in one single unit, one single PXI card. Now, our RTS solution would actually include some up and down conversion, so we would have our signal coming in from a radar, we would down convert that to an IF. This particular unit has around 200 megahertz of bandwidth, so we would put our IF somewhere in that 200 megahertz and capture a signal, maybe 80 megahertz or 50 megahertz of bandwidth. Within that, so here we have a zoom into that module. So we have our ADC capturing, we have some processing, and I'll show you the processing afterwards, but basically we can introduce delay, adjustable delay, and an adjustable frequency adjustment to the input signal. And then on the IF, we'll actually generate back out from here, and we can up-convert that and generate our signal. All of this is driven by other PXI modules, so we have a DIO module and a source module that's actually driving our LO for the down conversion and up conversion. This is a PXI chassis, in fact, and in fact the module that we have, we're talking about here is this module here. This is the M3302A. It's actually a 2-slot module, and we can actually see that we have multiple inputs and outputs for the ADCs and also the DAC outputs. The firmware that I'm going to show you actually, or the little application that we have here, was developed using the Pathwave FPGA development environment. It's a very nice user-friendly environment for development with FPGAs. So for the supported hardware, when the hardware is delivered and the firmware is, the basic firmware is already installed on the hardware. So for example, on this, we have repeaters or that will take in an input and feed that to an output, or we have basic AWG capabilities for the outputs. That's graphically shown within the pathway of FPGA as a number of input channels, and we have firmware blocks within that sandbox that can be used and are wired into the inputs and the outputs of our hardware itself. Now, when we want to implement our own firmware, we have a number of choices. There's a library of firmware already available, so we can take elements out of that sandbox and take other elements from the library and pull those in and unwire those up. Or we can create our own firmware code within that, and this environment supports both VHDL and Verilog development. And basically you can create your own elements which you will save to your library, and so you can reuse those as you wish. So that ability to bring in your own IP and introduce bring the instrumentation and marry that with the firmware development, enables you to make a very flexible input-output system. The hardware itself, so in fact we have also a little software application, a user interface running on an embedded controller. So this is an embedded controller. It's basically a PC. The processing performance is similar to a laptop PC, but it's embedded into the PXI chassis. So we have, this will be running Windows, and for this particular application, or this particular demonstration, we have a small user interface that was developed using Python that interfaces with the firmware that's on the, or that was created for the module itself. And as a demonstration, we can actually use the AWG on board of that module to actually generate our radar pulses. We actually feed that back into a digitizer channel on the same module. We adjust it in time and in frequency before regenerating that pulse and feeding that and capturing that on a further ADC. Now, in fact, what we can also do is we can take any one of our another source and generate a pulse that goes directly into the module, and we can capture that output also with a scope. So I mentioned latency in the past, and the latency really is the time between the input pulse being captured and a new pulse being generated. And in fact, what we see with this system, it's quite, as I say, it's quite simple in its capabilities, but we have a latency, a minimum latency of just around 400 nanoseconds. And 400 nanoseconds at the speed of light is equivalent to 120 meters. So that means we're looking at, we can simulate a target that is at 60 meters away from a radar system, and that's pretty close. So in fact, this is, I'm just going to show you a few videos of the actual firmware in action. We have this little GUI, as I mentioned, this is running in a Python script. We can actually define what we're going to generate with our own DAC. And once it's captured that waveform, we can adjust the frequency and we can adjust the delay. And we also have capabilities, some simple jamming simulation there. And this is how basically this is basically the function of receiving a pulse, and we can see that pulse here in yellow, and within the FPGA we are delaying that generation of a new pulse which is being generated. Similarly, we can capture that pulse and shift it in the frequency domain, and this is using a single sideband modulation, and so we can actually simulate a Doppler shift with a very simple frequency shift of that pulse. And here we can see just the enabling of a generation of a jamming signal, so we're repeating that pulse multiple times, and that can be controlled programmatically. Now, as I say, this is a system, this isn't an EW system. This is a little PXI system that can be used for students or to teach the concepts of EW or learn the concepts of EW. But really using simple tools that are available and usable on the benchtop today in a classroom. We understand that there is a lot of power in this, in these capabilities, and we've been investing a lot on development of this. And Phil mentioned, and I've mentioned already, this wideband signal platform. You can see the component parts of this is a down conversion to baseband, wideband, high-speed ADCs. We're talking about real-time data acquisition at up to around 12 gigahertz sample rates. So we can capture very wide signals. Once we've captured those signals, we can do a number of things. One of those things is we could do a very fast feedback. So we have capabilities for feeding that high-speed, wideband, high-resolution data to an FPGA to perform processing, much like we're doing with the PXI modules. And we can feed that to our AWG and upconvert that as directly. We can also do deep storage. So we could actually record a radar system or radar signal and keep that in storage, gapless capture to disk, and then we could generate that using the same system. We could spoof a system. So we have the capabilities within these modules of actually both modulating, generating, or streaming data, or all of the above. Now, in terms of cost, I mentioned before the requirements of deployed components, custom solutions. There are overheads beyond the purchase price of the hardware. But this particular system, using PXI for a lab environment, is very low cost and has very low development costs. Typically, a system could be a fully deployable system for a lab could come in under $50,000, compared to hundreds of thousands of dollars for a system that is designed specifically for an application and using customized components. So the 3302 is an example of what can be achieved with commercial off-the-shelf components. Hopefully in the next few weeks you'll be seeing more about the wideband solution platform from Keysight. All of these platforms provide a capability in terms of flexibility using FPGAs to provide the hardware accelerated processing, but the addition of instrument grade ADCs for signal capture and DACs for signal generation really enable realism in the radar target simulation. So hopefully that's been of interest to you. If you have any questions, I'll be happy to answer them. Otherwise, thank you very much, and I need to find Phil for some mathematics.